So we'll probably get started. Good morning, everyone. I'm Vijay. I work for Zylogic Systems and I head the automotive division over there. As part of our work at Zylogic Systems, we work with OEMs and tier ones in automotive industry. OEMs are basically car manufacturers, and tier ones are component suppliers for OEMs. As part of our work, we have built several test automation frameworks, primarily for embedded systems and automotive systems. So in this talk, I would like to share the insights that we have gained in automotive testing and embedded testing. I hope you'll enjoy the talk. Okay, so we'll start with the background in automotive, given that many people may not have a background in automotive. So basically, a vehicle or a car is actually a network of embedded computers, and these computers are responsible for various different functionalities within your vehicle. For example, providing driver information, navigation, playing music, controlling the locks, deploying airbags. All this is done through a network of embedded computers. And in automotive terminology, we call these embedded computers as ECUs, or electronics control unit. So these ECUs work in tandem to get the car functionality or vehicle functionality going. And in recent times, there's been a feature explosion in vehicles. Basically, your vehicles today can do a lot many things because of advancement technology and also increased in feature demands from customers. And traditionally, the testing and automation of testing for ECUs has been done through proprietary tools like vector VT system, DSpace, and so on. So these tools kind of prove to be insufficient for the complexity of modern ECUs, and that is where that's where Python and robot framework comes into play. They can work with existing tools, augment them, also replace them. So we'll see how that's possible through a series of demos. So for the demo, what we're going to do is we're going to take a digital cluster and use that as an example for demonstrating how automation can be done. And we'll show what are the ways with which we can automate the device in the test. And we'll see how to write test cases in robot framework. So starting with the digital cluster that we have, this is the digital cluster that we're going to test. This is something that you can purchase from Amazon, and you can connect it to a vehicle. So it is called a HUD digital cluster. So it has this display. It's a digital display where you can see the various gauges, and then at the top there are buttons through which you can access the menus in this system. So these digital clusters can augment your existing dashboard. That's one way of doing it. There are also variants of this called AR HUDs, augmented reality HUDs, where they project this display onto your windshield, and they can provide augmented reality overlay on your windshield itself. So we are taking a smaller version of this, and then we're going to demonstrate how to test this system. So how do you connect the system to your vehicle? Basically, this system has an OBD2 port through which it can interact with the vehicle. So your vehicle has an OBD2 port. So that's the photo of my car, and at the bottom near the steering wheel, you have this OBD port, and there is this connector over there. You can connect this device to that OBD port, and then it can get the data from your vehicle and display it on the digital cluster. So how does this work, right? Basically, the OBD2 port is like any of your USB port in a PC. It can be used for connecting peripherals. And the protocol that's used in this OBD port, among the various peripherals, protocols that are available, there is a protocol called CAN. It's an automotive protocol, and that is available in this OBD2 port. So this is a diagram of how a CAN bus looks like. So we said that a vehicle is a network of embedded computers, and these embedded computers are connected together through a CAN bus. And CAN, as we said, is a bus, which means that all the nodes are connected into a single set of signals. And when a node transmits data, all the nodes receives the data. So it is a broadcast transmission. It's similar to UDP broadcast, but it is more a low-level interface. It's uses an 8-byte messaging. So a message can be maximum of 8 bytes, and there are different formats for these messages. So one message format might send out a speed information. Another message format may be used for sending seat belt information. Another message could be used for sending door lock information, and so on. So these messages are broadcasted on the CAN bus, and then any consumer that wants the message can consume this and then display it onto the screen or take an action based on it. So for example, a speed sensor might be periodically sending out a speed data on a CAN message, and then the dashboard might consume this message and then decide to display it to the user. Similarly, you can say that the door lock that is there, and if the door is not locked, then it will be advertising that message over network, and then this will be taken by the light controller on the vehicle, another ECU, and it will decide to turn on the light or turn off the light as required. So this is how a CAN bus works. Now let's see, given this digital cluster, which has these interfaces, how do you test this ECU? Right? So let's start by understanding how you would test this system. So in our device under test, there are basically 4 interfaces. One is the display. There is a CAN interface over the OBD port, and there are 4 buttons at the top, and there is a power, which also we consider as an input to the system. And basically, we want to control these input interfaces through a hardware-software combination, and we want to be able to capture the output from the output interface and be able to make assertions on the output. So this is basically what we want to do. For each of these interfaces, let's see how this can be achieved. So let's start with the display. So the display, of course, is used for displaying gauges like speedometer, odometer, trip meter, and so on. So you could use a webcam to capture the contents of the display, or you could use something like a Raspberry Pi camera. It's an alternative that you use. In this case, we are going to use a Raspberry Pi camera to capture the display of this device. After we capture the display, then we use existing image processing libraries like OpenCV and Tesseract to be able to interpret the content of the display. So with this hardware and software in place, we have these keywords, or we have these functions like take screenshot to capture the screen contents, crop it to the required region, we have a crop function, and then we have an OCR function that can convert image into text. So this is a bunch of functions we have implemented to interact with the display. Then we have a set of APIs to interact with the buttons on the top. So this is again a hardware software combination. So the hardware we're going to use over here is called a solenoid. The solenoid has 3 parts. One is a spring. The spring is connected to a metal plunger. The plunger is by default retracted because the spring is holding it. And then there is a coil of wire which, when energized, acts as an electromagnet and will pull in the metal plunger. So when the coil is de-energized, it will get demagnetized, and the metal plunger will go back to its previous position. By putting a button in front of the plunger, you can actually control the button pressing and releasing it. So we have a bunch of Python APIs implemented that can, we have, of course, the solenoid, and then we have a bunch of Python APIs that will control this solenoid. So we have a short press and long press functions to press a button for a short period or a long period, because based on that, the device will have different behaviors. So that is how we control the buttons. And then coming to the OBD interface, we said that there's a CAN bus. Now, of course, the PC does not have a CAN interface. So what we do is we have a USB to CAN adapter that can take these CAN messages and provide it to PC, or take messages from the PC and then provide it to the device under test. So basically what we're trying to implement is a vehicle simulator. The OBD to the digital cluster connects to a vehicle. We don't have a vehicle over here. So the test PC acts as a vehicle simulator. It is going to send CAN messages to the cluster to simulate a vehicle's messages. So we have these functions implemented: start vehicle simulation, stop vehicle simulation, and also set vehicle parameters. You can set various parameters like odometer parameters or speed parameters and so on. So that's the API that we built on top of this. So in Python, we have a Python CAN module that can be used for interacting with devices like a CAN to USB adapter. So that's something already available in Python, and we're building on top of it. And then finally, you'd want to turn on and turn off the device in the test, because you would want to generally put it in a default state before you start testing, and sometimes in a test case you want to bring it back to its default state. So we have again APIs to do it. We use a relay hardware to control the power to the device in the test. So this is the test setup that we have now. We have the device in the test at center, and then we have these other hardware components connected to your test PC. So that test PC is my laptop. And essentially the test setup looks like this. So the oval shape is the device in test, and the blue color rectangles you see are the solenoids, and that's the relay board. So the solenoids are also controlled through the relay. And at that top corner you see the CAN to USB adapter. So what's not clear over here is the Raspberry Pi and its camera. Okay, so we also have the setup over here, and I have it being streamed to the my laptop. Okay, so now let's look at how to write a test case. So let's say I want to write a test case in which we want to verify if the digital cluster is displaying the speed that is being transmitted by the speed sensor. So this is the test case, and here we are verifying when the vehicle is transmitting the speed information, the vehicle speed sensor is transmitting 100 kilometers per hour, is the speed gauge displaying the value between the range 100 to 105. The reason why we are checking between 100 and 105 is because there are government regulations that indicate the speedometer should actually display a value higher than the actual speed. Okay. So this is how a test suite looks like. Before we go into test suite, I will first run it. Let's see it in action first. So this is how you would run the test suite. So sleep please, just to make sure that I'm able to switch to the live stream. Then robot is the command, test v2 is the robot test suite name. So we are turning on the display, turning on the device first. You heard a click sound, that was actually the relay turning on. So the speed was advertised, and now it's displaying the speed on the screen, which is captured by the camera, and then it would process that region, convert it into text, and then compare it with the expected value. So this is what our test case was doing. So let's look at the test suite itself first, and then let's look at the log file that was generated. So this is the test suite, test v2.robot that we had written, and it has one test case. So there's a test case section where this test case is defined, and you can see that test case is defined in plain English. There's no, it looks like it's plain English, but in fact it's actually what we call as keyword invocations. The keyword is used to perform some action. So here there are 4 actions being performed, and what each of this keyword does is defined in the keyword section. So the keyword section defines each of these keywords, and these keywords are defined in terms of other keywords. So there is these high level keywords in your test case, they are defined in terms of low level keywords, and it keeps going on like that till you hit a point where you want to invoke a Python function, and the Python function can be invoked as a keyword in robot as well. So we had these keywords called take screenshot. So when you want to get the displayed speed, first you call take screenshot. This is actually will result in a Python function being invoked that we already have from a library. Then we do a crop, we do an OCR, we convert it to integer, and then we then compare it to the required speed. So the Python libraries can be imported using this library in the settings section. So we say I want to use this library, and within robot you can use that Python function by invoking it by its name, or you can actually drop the underscores, and the case comparison is also dropped. So this is how a test case is written. Now, a test case can, like we said, is a sequence of keyword invocations. Some of these keywords are action keywords, and some of these keywords are actually verification keywords. So a test case fails if any of the keyword fails. A keyword fails if it triggers an exception. So if any of these action keywords triggers an exception, then the test case would fail. So these verification keywords that are at the bottom, they would raise an exception when the comparison fails. So that's how it would decide whether test case is passed or not. So there are verification keywords at the bottom that would raise an exception when they fail. The comparison fails. So moving on. So let's say I want to add more test cases. So in the test case section, you can add another test case. Now I want to do for vehicle speed 100 and vehicle speed 50. Now when you do this, you don't have to re-implement each keyword again, because there's a new keyword. You don't have to re-implement it. You can make your keywords generic. Previously, our keywords look like this. So when you want to verify the displayed speed, you get the displayed speed, and then you are trying to compare it with a value. But then when you define the keywords, you can use what are called embedded arguments. And these embedded arguments can be extracted from the keyword invocation, and then they can be used within your keyword as variables. So that is something that robot allows you to do, so that you can write generic keywords. This is one way of passing arguments to a keyword. There are other ways of doing it. Now, what you might have observed over here is that robot framework tries to make test case development look like you're writing plain English, and that's intentional. You can write test cases in plain English. The idea is to make writing test cases easy for domain experts. Now, for people who are coming from a web background, it might not be very obvious that you're going to have two sets of people, one for development, another for testing, or because in the automotive world, there are domain experts, and these domain experts are not necessarily familiar with programming. They're not necessarily programmers. And so for some of the ECUs that we work with, there are about 5,000 requirements resulting in 15,000 test cases. So understanding what the ECU is supposed to do itself is a job in it. So writing these test cases is done by a separate team, and automating test cases is done by a separate team. So robot framework provides you a way of separating this into two parts. One is for test case development, and that is for test automation framework development. The automation framework, of course, is the hardware and software combination. And then there's, with that in place, let's see how you'd write another test case. We'll probably run that again. So there's a version 3 of this test suite where we have two test cases now. So the first test case is going to check for speed 100, another for speed 50. And you can see that we have these keywords that are generic. They accept the value to be used for comparison as an embedded argument, and then that you can later on use in a variable here. Let's try running this, and then I'll show you the robot log. So we'll run two test cases. The first test case is going to set the speed at 100. The next test case is going to set the speed at 50. So it is displaying the speed of 105. Now we go to next test case. Every time you switch to a new test case, we turn off the device, turn it on again, and then we advertise the new speed value. Okay, so what robot does is When it completes a test execution, it provides what is called a log file or a report file. So here in this log file, you can see there are two test cases listed, one test case for the 100, another for 50. So this log is a crucial element in test execution. So among the other things, it tells you which of the key test cases passed, and if a test failed, it would tell you which particular keyword failed, and then you can go and check within the keyword what caused the failure, so it can expand further. So this is where we're verifying the displayed speed. So you can say get displayed speed, we're expanding again, so the keyword definition can be expanded, and we can go to each of these keywords. In this particular keyword, the keyword is logging additional information into the log file. So when we captured the speed and cropped it to the required region, this was the image that we got. So if case, let's say this test failed, you could go and look in the log file and see what exactly was in the image when the failure happened. Right. So that's the usefulness of this log file, and generally keyword developers put in additional information that can be used post the test execution. So let's now try adding another test case. Let's say I want to check the version of the software that's running within this digital cluster. There is an about screen in this software. If you go to the about screen, it displays the version. So what we're going to do is we're going to enter the about screen. For that, we're going to write a keyword to enter the about screen. So it's called entered about screen. So that keyword definition looks like this. You're going to long press the escape button. That will take us to the menu. The long press of the escape button takes us to the menu. We repeat the keyword 6 times. Short press down. So you press down, down, on. There's a menu, it comes. You can then press the down button 6 times. The 6th menu item is the about screen. And then you say a short press of OK, it enters into the about screen. Now after we enter the about screen, then we again do this image processing on the captured screen data to check if the displayed version is 1.1.6. So this is how the test suite looks like now with this test case added. So there are 3 test cases now, one for the speed of 100, another for speed of 50, another for the software version. So let's try running this test suite now. This is test V4. So you can also look at the relay. There's an LED on the relay that indicates that the relay is turned on. So that relay is for turning on the power. And the LED that you see blinking over there at the top is actually the CAN messages going in and out of the system. So this is for the speed of 50. And finally, we have the test for a speed of, it's for the software version. So those are the solenoids. You can see they're moving their arm. And this particular solenoid is not supposed to be used for with these buttons, but when I wanted to purchase solenoids, these were the ones that were available. So they're just too powerful for this particular use case. Let's see if we have all the test case passing. Yeah, it's passing. So let's look at the log file, software version. So you can see the software version. It took a screenshot after entering this about screen. So, and this is the cropped version. And we did an OCR on it, and we get the value 1.1.6. So that's basically how you would write a test suite to, or build a test framework and write test suites to validate ECUs. So the key takeaways from what I want people to get on stock is that your vehicles are getting increasingly complex, and testing is becoming harder. and there is a lot of scope for Python developers to work in this area of automotive testing. So it is generally achieved by a combination of hardware and software tools, and Python, being the universal glue language, can work with existing proprietary tools and open source tools to achieve complex scenarios, drive the system to complex scenarios, and verify the device in a test. So that's basically what I want people to take away from here. And these are the credits. I'll wait for a couple of seconds for this to be seen. I want to thank my colleague Dhanasekar, who helped me with the mechanical setup. And moving on, these are pointers to further reading. The many of the modules that we've written for test automation, they are available from this GitHub project. And the demo test suites that I've shown today are available from this other GitHub project. And these are for Robot Framework and for Canon OBD2, further information. So thank you for your time, and if I have time for questions, I was told that the people have to come to the front for questions. Sorry about that. You want the last one to finish? I was working the whole day for it to pass.
Yeah, let's just put 7 there.
I mean, you wanted to put 7. Okay, let me see. 1 second. I'm not sure if it's taken as embedded argument. Give me a minute. Yeah, so it is taking as embedded argument only, right? Yeah. So yeah, it is something that I can do. I'll just run that test case alone. So what I'm doing is I'm passing an argument to Robot Framework to run a particular test case alone.
While that's running, a quick question: is every sensor in every vehicle tested, and how does that happen at scale?
At scale, every sensor. So we are trying to test one ECU over here, and that the ECU that generally we work with are called cockpit electronics. These are ones that have advanced interfaces like Wi-Fi, Bluetooth, displays, touchscreens, and so on. So, so what we do is, I'm not sure about the scale over here, but let's say a vehicle is built out of hundreds of ECUs. So generally, what OEMs do is they get these ECUs and then they put it on a test jig, and then they run the test suits on the test jig. So then we have these complex ECUs that have to interact with a bunch of other ECUs and also maybe simulate some of them. So they are also sitting on test jig, and then we have these test hardware connected to them that will drive these. So this is for one vehicle design, not necessarily manufactured test of all ECUs.
Yeah. I'm so sorry to cut you, Vijay, but we are really out of time.
Okay.
We are over 1 minute.
Yeah.
So all of you, if you have any other questions, please feel free to connect to Vijay outside of this room or after this talk. But we really need to move to the next